Okay, hello everyone. My name is Arcana, and today I'm excited to present my research paper, Modifying Dijkstra Algorithm for Efficient Sorting, a, a theoretical and experimental explanations. This research began with simple yet fundamental questions that we can borrow an idea from one domain of computer science, like graph theory, and apply it in another to create something new and useful. We all know that sorting is a fundamental operation, but have we ever considered borrowing an idea from the world of graph transversal, like Dijkstra algorithm, to perform a sort? Well, this is the foundation of my research. The core idea was to adapt the central mechanism of Dijkstra algorithm to sort data. From this, my research objectiveness become clear. First, to define a new algorithm that personally I call it Dijkstra inspired sorting, or DIS. And second one, to analyze it theoretically, and most importantly, to test its performance in real world to see where it stands against the established algorithm like quicksort and merge sort or heap sort. So, what exactly is DIS algorithm? The concept is very simple and elegant. It doesn't use the entire graph logic of Dijkstra, but instead still its most powerful component, the mean priority queue. The process has two main phases. First, we insert all the unsorted elements into the priority queue. Because it's a mean priority queue, the element with the smallest value automatically gets the highest priority. The second one, we simply extract the value or the elements from the queue one by one. The elements that come out that will naturally be in sorted order from the smallest to the highest, to the largest. In essence, functionally, DIS is an implementation of the heap sort algorithm, but it leverages the convenience of the STD priority queue component that available in the C++ standard library. Before we look at the experimental result, let's see what the theory tells us. Based on my analysis, DIS has a time complexity of O n log n in all cases, best, average, and worst. This makes it incredibly stable and predictable. However, there's a trade-off because we use auxiliary data structure to hold all the elements in space complexity. Its space complexities become OM. This is different from an in-place heap sort, which is very memory efficient, but it's comparable to merge sort. My main hypothesis before the experiment was this DIS will be predictable, but likely not the fastest. To prove the hypothesis, I designed a rigorous experiment. I implemented DIS and three main comparison algorithm in C++. I test on dataset up to 100,000 elements to truly test the resilience of each algorithm I use for data types. Random data for the average case and the sorted and the reverse sorted data to test worst case scenarios. The metrics I measure were execution time and peak memory usage. Now let's take a look at the result. For random data with 100,000 elements, the outcome is very clear. Quicksort is the champion, finished in just 34.7 milliseconds. DIS, as we can see, comes in last at 105 milliseconds. This confirms that in the average case, the abstraction overhead from a standard library prior to Q from C++ make it slower than other more optimized algorithm. However, the story completely changed when we feed it sorted data. This is where we see the catastrophic failure of Quicksort. Its execution time skyrocketing to nearly 90 seconds. This is a perfect demonstration of its O n square worst case complexity. And this is where DIS shows its true strength. Its time remains incredibly stable at 101 milliseconds. It is completely unaffected by the initial order of the data. This is what I call reliability. We see the same pattern with reverse sorted data. Quicksort fails again, taking about 56 seconds. Meanwhile, DIS remains consistent at 141 milliseconds. Interestingly, merge sort is the fastest in this scenario. But the main point remains, DIS proves to be incredibly reliable, but no matter how bad the input data is. So, what can we conclude for all this data is there is a clear trade-off. Dijkstra-inspired sort, DIS, offer absolute reliability. Its performance is guaranteed O and log n. And it's very easy to implement. However, its weakness is that it's slower in the average case and requires ON memory. On the other hand, Quicksort is a speed champion, but it comes with the risk of a massive performance failure. It's like a race car that's incredibly fast on straight track, but can completely break down on a sharp turn. The choice of algorithm ultimately depends on what we prioritize, average case speed or guaranteed reliability. In conclusions, where does DIS actually fit in? This research shows that DIS is not a new best algorithm in general. Instead, it fills a very important and specific niche. DIS is the right choice when two things are priority. First, safety, when you are building a critical system that can never afford to slow down unexpectedly. Second, its convenience when you need a reliable solutions that can be implemented quickly using standard library components without writing complex code from scratch. Essentially, by choosing DIS, you are trading peak speed and peak memory efficiency for something very valuable, absolutely reliability, and easy of implementations. That's the conclusion, that the presentation of my research. Thank you very much for your time and attentions. I would now like to open the floor for any questions you may have in the comment below. And yeah, thank you. And until then, stay do science.